Namaskar and welcome to Easy Classroom. For today we will be learning n-bit parallel adder. For n-bit parallel adder we will be actually adding n number of bits, and with the help of full adder we will be actually adding those things, because full adder has the tendency and has the capability to propagate the carry information for us. For that reason, actually we are designing this actual circuit with this full adder. Now let us consider about the points that we need to get in order to understand this kind of logic systems. Let us understand. So it can add n-bit number as it is. The name says it can add n-bit binary numbers. It uses the full adder circuit. That is the most important thing. We can have and the number of bits that are going to be added is equal to the number of full adder circuits that are going to be incorporated in this kind of system to actually add. And it is used in where? In ALU systems. Now there is a drawback, and we will not be going into the drawback as of now, but let us understand these things. Say for example, we are to add, so in this case there are 4 full adders, so we can have 4 numbers. This is for A and this is for B. So 1 1 0 1. Okay. Now this is for our S, and say for example this portion is for our carry. Okay. Since there are no carry over here for this we are going to actually have this 4 bits, 4 portions, and we are going to add these things with the help of this combination thing. Let us understand first, for this is A0 B0. Why is A? That means this is A0 and this is B0. This is A1, this is B1, this is A2, this is B2, this is A3, and this is B3. Okay. Now let us understand first. Since there are no carry at the beginning or of anything of this, so the carry in, C in will be 0. So that means here the C in will be 0. Okay. Why the C in is 0 and why we are actually keeping this in this format? Why we need C in over here in the first place? Let us consider this. We need to add 16-bit or 32-bit numbers. So we can cascade this 4-bit parallel adder with another 4-bit parallel adder, and this C in for the next parallel adder, this C in will be this C out of this C in. Understanding? That's why we are actually using this C in as 0, and we are actually giving this C in as an input to this entire thing. Understand? Now let us find out what is the value of these things. So 1 plus 1, we will be getting 2. That means 0, and there will be a carry, and the carry will be moving upward. Okay. So 0 plus 1 is 1, and 1 plus 1 0 is 1. That means 1 over. There is 0 carry. Okay. So this is sum. So this is S0, this is S1, and somewhere it will be S2, and somewhere it will be S3. Okay. So this is 1, and there will be 0 carry. So this 1 1 equals to 0 with a carry, and if it doesn't get anything, it will simply fall down as C out. So if we have if the Cout value is Cout x1, we consider the entire value. This is our entire sum. If we will consider that, okay, if Cout is 0, we don't consider that, right? We don't consider that. If we do also, say for example, we have this, since, so this is my actual number, entire thing, this is my entire thing, that is the sum, and say for example, we have this. So what will happen? These MSBs will not be actually considered. What will be considered? This one. So if we do consider even for the 0, it will not be taken into account, since 0 in MSB doesn't have any meaning, right? So this is how we can add 4-bit numbers, and we can calculate on the basis of Cout what will be the actual sum. If it is 0, then the sum will be of, actually the sum will be of n bit. The sum will be of n bit, and if this sum is, then it is n plus 1 bit. Why? Because we have 4-bit, and if it is 1, then we have extra 1 bit that is going to add in the sum. That's why it is n plus 1 bit. And if it is 0, then we will not be taking into account, so n bit will be the sum. This is actually the whole thing. Now, what are the problems that we have to take into account while we are actually designing this kind of logic system? The first problem that arises is this Cin will have to wait for this adder to perform its task. Why it is so? Because it is actually dependent on this, and Cout of this adder will be the Cin of this adder. So in every case, every adder is going to be delayed, and this is actually propagation delay of carry information. Okay, so sum, for sum, what will happen? Sum equals to A, B, C. This is our sum logic. And for carry, A, B, and this is XOR operation. And for carry, we have this. Since we all know in full adder circuit and half adder circuit how these things actually happens, so this is how we can add n bit numbers with n bit numbers using n bit parallel adder. Now, how this comes, we know as A0, B0 and Cin get into full adder. What will happen for the sum? For how we actually add A XOR B XOR C, we have done it in using K maps and truth table and all that things. For carry, what we are getting is this. This is actually the carry output of this entire thing. This is how we can get. I hope you have understood this thing.